Hey guys, welcome to my channel. I'm LeetCoder. If you guys are new to my channel, I pretty much do LeetCode style questions and I explain things in the simplest way possible. Today we have a pretty interesting problem, guys, that I'm very excited about. So let's get into the problem statement, right? So the problem is called validate binary search tree, right? So it says given the root of a binary tree, right, determine if it is a valid binary search tree. Okay. It says that a valid BST, right, is defined as follows, right? The left subtree of a node contains only nodes with keys less than the node's key, right? And it says the right subtree of the node contains only nodes with keys greater than the node's key, right? It says both the left and the right subtree must also be binary search tree, right? Pretty much what they're saying, guys, you know what I'm saying? They're saying that for every node, right, everything on its left side is going to be smaller, right, and everything on its right side is going to be bigger, right? So this is what it has to fall under, you know what I'm saying? So yeah, guys, so and it also says that all the subtrees, right, within that tree have to be valid as well, right? So the whole tree have to be valid, guys, you know what I'm saying? So it's a very good problem to do. So let's go through those examples real quick, okay? So now we're given this binary tree, right? So 2, right? 2 is the root, right? So now everything on the left side of 2 has to be smaller, right? Everything on the right side of 2 have to be bigger, you know what I'm saying? It's likewise the same thing, right? Everything on the left side of 1 has to be smaller. Everything on the right side of it has to be smaller, right? And everything in the left side, same thing. Every node, everything on its left side has to be smaller, right? I'm saying. So the way we're going to end up solving this problem, guys, we start from the root, right? Then we pass in some parameters, right, to every node, right? Every children, right? So 2, right, is gonna tell a 1, right? Hey, you cannot be you cannot be greater than I am, right? There should be no numbers that exist in that subtree, right? In that subtree that's greater than 2, right? Greater than or equal to 2, right? There should not be that, right? If there's 1, right, we're gonna end up returning false. I'm saying, because we give it that boundary that says, hey, every number on my left side should be smaller than I am. So that's what the thing said on the constraint that were given to us, right? It told us explicitly less than, right? And then yeah, so 1 checks its subtree as well, right? And there's nothing there, so they both return true, right? And then 1 says, all right, cool. On the left side, 2, you don't have to worry about anything. You're good, right? So 1 returns true to 2, right? And then we go to the right side, right? And then 3 does the same thing, checks all of its subtrees, right? And then returns if its subtrees are also valid as well, right? So 3 is like, all right, cool. I'm greater than you are, so you're good, right? You don't have to worry about a thing. So now we get true and true from both sides, and we return true to the color, right? So let's do this quick example really quickly, right? So this problem is a very good one. So now 5 is like, all right, cool. There should be no numbers that exist that's greater than 5, right, on my left side, right? So 1 does a check, right? 1 does the same thing. 1 checks. It says, all right, cool. You're good on the left side, man. Now go check the right side, you know what I'm saying? So now we're on the right side, right? 4. So 5 is like, all right, cool. There should be no number that's smaller than I am. You know what I'm saying? Smaller than or equal. So now 4's job is gonna be able to check that, right? So once we get to 4, guys, 4 is smaller than 5, and 4 is on the right side of 5, right? It doesn't fit that constraint that was given to us, right? Therefore, that's not a valid boundary search tree. So we return false, right? Because 4 doesn't fall within that boundary between 5 and infinity, right? So 5 told 4 that, for you to be valid, right, you have to be greater than 5, right? It could be anything from 5 to infinity, you know what I'm saying? Not including 5, right? Anything greater than 5, right? So this subtree is valid, right? But no, since 4 is smaller than 5, it makes the tree not valid, guys. You know what I'm saying? So you see 3 is smaller than 4, right? And 6 is greater than 4, right? This subtree alone will be fine, but that's not how we do it. The whole tree has to be valid, right? So 4 did a bad job being on the wrong side, right? So we return false. So as you guys can see, the way we're going to solve this problem, guys, is by pretty much giving our children, right, some kind of constraint, right, some kind of boundary. Say, all right, cool. For your site to be valid, you have to fall within that tree, right? And all your children as well have to fall within this boundary as well, right? So we keep passing boundaries every time to our children, guys, and make sure that our children, right, fall within those boundaries that we give them. And if they do, right, everything's fine. If they don't, right, return false. They say, all right, there's a part of the tree that's not good at all. That's kind of messed up, right? So that's why we end up doing that. So hope you guys were able to follow with the thought process and the thinking that I was trying to help you guys understand before I went into the code. So right now, yeah, so let's get into the code. So yeah, guys, right now we're just gonna do this really quickly, guys. So I'm saying, so right now, the code is gonna be pretty good. So we're gonna do it the same way we did it for so we're gonna use a kind of helper function, right? So for the helper function, what we're gonna do, right, we're gonna pass in the root, right? And then I told you guys we're gonna also pass in, right, the boundaries, right? Every node we're gonna pass in the boundaries. So right now, initially, right, the values, right, it's gonna be really big numbers, right? So the min, right, the lower bound, right, starting from the root, right, it could be any small number and any big number, right? So we use long. Okay, I'm gonna tell you guys why we use long, right? Long, that max value. All right, so now just do this real quick. So this function is gonna be pretty much the same thing as it's gonna return a Boolean value, right? So now after we told them that we're gonna accept a root, right? And also we told them that we're also gonna accept a min value to represent the minimum. All right. So the lower bound, right? The min represents the lower bound, and the max represents the upper bound. You know what I'm saying? All right. So that's what we get. Yeah. So yeah, guys. So why we use long? The reason why I use long, right? Because for certain test cases they use integer that max value and integer that min, right? So to pass those test cases, guys, we use long to be able to pass them. And in the problem statement, it didn't say that using long would be a bad idea, right? Like illegal. So we're allowed to use it. So to make our lives easy, we use long, right? To get a really big number. So now, guys, so if a root is null, right, we're gonna return true, right? That means we probably got to a path that's good. So we're gonna return true, right? So if there is no true, right? So now, guys, the next thing that we're gonna do, right? If we get to a node, right, that's not within the bounds that we give it, right? So let's say that we give it. So let's say the root, right? The particular root that we're at right now, right? Because I told you we're gonna visit the nodes, right? If a root, right, is so if a node is greater than or equal to the maximum value that it's allowed to be, right, then that's not good, because we give you a maximum for a reason, right? You cannot reach that maximum, right? That's why, guys, if you don't fall within that range, right, that means that you're not a binary search tree. I'm saying, so or, right, root that val, right, is smaller than or equal to the minimum number that we told it that it's allowed to be, right? So the next thing that we can do, right? So if the root, this particular node's value, right, is not within the bounds, right, we're gonna end up returning false, right? So now, if it's a good path, right, we're gonna recursively keep checking on left, right, on left and the right. So left, right, we pass in our so the minimum value from the left side is still gonna be the current minimum, right? And then the maximum value, right, the upper bound now is gonna be the current root that we're at right now, because I told you guys, right, everything on the left side of a particular node is gonna be smaller than it, right? So that's why we do that, right? Because we know that now, since everything has to be smaller, right? So that means that the node that you're at right now is the lower bound, right? So that's like doing we had 2, right? 2 is like, all right, cool. I'm checking my left side, right? So the lower bound could be anything, right? Could be from anything, right? But the upper bound is gonna be has to be 2, right? It cannot be greater than 2, right? I'm saying, or equal to it. So now, yeah. For you guys, and then we do the same thing, right, guys? We go right, right? We're gonna pass in some parameters as well, and it's gonna be very, very good. So what's going right? So now that the minimum value, right, is gonna be the current root that we're at right now, you know, because everything on the right side, guys, have to be greater than the root that value, the current node that we're at right now, and then it could be anything from 5, right? Anything from the root value, right? Not including it, right? And beyond, right? I'm saying has to be greater than it, right? And then, guys, once we get the answers from the recursive calls, guys, we're gonna return the left and the right? They both have to be valid, right? Both my left side and my right side have to be valid in order to consider this to be a valid binary search tree, guys. I'm saying this is a very, very good problem, guys. You know, I hope I was able to explain to you guys the thought process of the code, right? So let's see if we pass some test cases, guys. What I'm saying. All right, we passed that small test case. Let's see if we pass all the test cases. Perfect, guys. We're able to pass all the test cases, guys. No, yeah, guys. I want to thank you guys for taking the time to watch this video. If you guys found value, give me a like, and also if you guys are new here, make sure to subscribe because I'll be doing a lot of other videos just like this one. I want to thank you guys for taking the time to watch this video, and I'll see you guys in the next one.